Okay, hello again. Lesson 8, as promised earlier, I'm going to talk about shapes of simple molecules and why certain molecules, like for example ammonia, and I'll discuss water in a minute as well, have the shapes that they have. Again, going back to what you learned about electronic configuration, you see, on its own right, it's important to be able to write electronic configuration of elements, of ions, whatever. But then you also use them as a tool to actually explain something maybe slightly more important or slightly more challenging. One of them being shapes. That many students in the past that I've had always kind of, particularly if I ask them 6 months later about shapes, they find that topic a little bit more challenging because there are quite a number of things that you have to adhere to and focus on. If somebody says, for example, what is the shape of ammonia, NH3, what are the things that you have to do in succession in kind of small bits of information that have to follow one another, the one after the other? How would you scaffold your answer? And when somebody says, what is the shape of ammonia? You cannot straight away, it's pyramidal, it's trigonal pyramidal. I mean, where did that come from? You have to arrive at that answer, having answered other bits and pieces that are relevant to the question. So for example, NH3, the first thing that you have to write to actually establish what the shape of ammonia is to write the electronic configuration of nitrogen. It is nitrogen which is attached to 3 hydrogens. Hydrogens at the other end of nitrogen don't make any angles, bond angles. It's nitrogen in the middle that does. So you have to write the electronic configuration of nitrogen. Now let's see what we see. Obviously it's atomic number 7, so it's got 7 electrons in its shells. So its electronic configuration would be 1s2 in the first shell. We are never bothered with inner shells. The only thing that we are bothered in anything, in bonding, in chemical reactivity, even in shapes, is always the outer shell electrons. Remember that. So what do we see in the outer shell? We see in the outer shell is 2s2, 2px1, 2py1, and 2pz1. Or 2p3 if you like to put it that way, in slightly shortened version. So why did I encircle 2s2? Because 2s2 in the second shell is not involved in any bonding, and it is referred to as a lone pair of electrons. And a pair of electrons that, if you can put it very crudely, they are sitting put in one position, and that position on nitrogen, imagine, has a very intense electron concentration and therefore negativity. We'll come to that in a minute when we talk about repulsion. So when I write the electronic configuration of nitrogen, do I see if there are any lone pairs? Yes, I do. 1 over there. Okay, well done. Let's move on. And then we have to talk about repulsion forces. Repulsion forces. Let's draw a nitrogen here. Let's again choose a different color so it becomes. So there's your nitrogen. There is your lone pair. And these are the bonds that it is forming with hydrogen. There's your ammonia. So these are the p orbitals. They have 1 electron in each. And then hydrogens come along, electronic configuration of 1s1. Remember, they've got 1 electron. So they bring their electron as well. They pair up with these guys. And then they are, a pair of electrons in each bond. But these bonds are referred to as bonding pairs. Pairs as in pairs of electrons, Obviously, these bonds are also comprised of 2 electrons, aren't they? 1 from nitrogen, 1 from hydrogen, covalent bonds, remember? But there is a difference between these electrons, these 2 electrons in each of these bonds, and those 2 electrons. These electrons there are highly concentrated in one area. They are very, very negative indeed. These electrons over here are kind of slightly more distributed and scattered. There are still a pair of electrons, we get that. But I always tell my students, it's like if somebody puts, I don't know, half a teaspoon of salt on your tongue, you feel, oh my God, you know, it's so so bitter. But then if they put the same amount in a glass of water and you drank it, you wouldn't even feel that it was salty. It's the same amount, but then it depends how condensed and concentrated it is, isn't it? So if you've got a pair of electrons that are sitting there doing nothing, all they do is that they've got negative charge, right? So what do they do to other negative charges? What do they do to other clouds of electrons that are around them? It's quite obvious what they do. They repel them. They repel them. But then the repulsion, now we are arrived at the point where we have to talk about repulsion. That lone pair repels these bonding pair in there, here, and also that one. So if I say that there are 3 lone pair bonding pair repulsion, okay? There are 3 of them, 3 lone pair bonding pair repulsion. But then these bonding pairs also repel one another. That one repels that one repels that one, and that one at the back repels the other guy at the back. So there are 3 bonding pair repulsions as well, right? And as a consequence of this, if that lone pair didn't exist, these 3 bonds will just repel each other, right? And then the bond angle between them on a flat surface would be 120 degrees, wouldn't it? 360 divided by 3. But then since, imagine the knuckle on my hand is a lone pair. That lone pair pushes these bonds down. And it pushes them down. So they are not flat, they turn pyramidal. And what is the base? The base is triangle, isn't it? So we say it is trigonal pyramidal, because we could have pyramids with a square base, yeah? Square pyramidal as compared to trigonal pyramidal. If I'm not mistaken, you can still write pyramidal and you would get the mark, yeah? So, but it is, that's why in some mark schemes, trigonal is written in brackets, but pyramidal. Pyramidal. I have to write a little bit slower on these boards, otherwise it won't register. So the shape is pyramidal because of the role of a single lone pair there. Okay? And then it's, they want, imagine they want to be flat, but then that lone pair is pushing them down. And the forces of repulsion from the top is greater than the forces of repulsion from the bottom. And therefore the whole thing turns into a kind of a flat pyramid. Not very, very tight, flat kind of pyramid. And therefore, and then the other thing that you have to talk about is, after you've talked about the repulsion forces and what they are, then you have to talk about the bond angle, yeah? So the bond angle, when you have 3 bonds and 1 lone pair, is 107 degrees. Okay? And then the shape is trigonal pyramidal. So how many different things did you have to do in the right order? In, scaffolded version, bits of information that are all interrelated and ultimately allows us to come up with the right answer. Electronic configuration. Are there any lone pairs out there? In fact, your appreciation and understanding of what lone pairs are. And then you have to talk about repulsion. Then you have to talk about bond angle, and ultimately you have to say the shape is whatever. Now, it becomes interesting that, for example, if you have a molecule, let's say you've got phosphorus there and it's attached to chlorine. And somebody says, so what is the shape in that region? What is the bond angle in that region? And you're thinking, phosphorus? Well, if nitrogen is 2s2, 2p3, yeah, then phosphorus is in the next period, so it would be 3s2, 3p3. You see? So even in phosphorus, you have still 1 lone pair. So the shape would be the same. And the interesting thing is, it doesn't matter what they are attached to. Whether they're attached to chlorine or hydrogen or butyl or whatever, we don't care. It's phosphorus. that has one lone pair of electrons. That's one, not that one, but it works in exactly the same way. And therefore the repulsions would be the same. Therefore the bond angle would be the same. And therefore the shape in that particular area would also be the same. If I was going to talk about water and other molecules, this clip would be too long, so I'm going to stop now. And maybe I'm going to give you the idea of what the shape of water molecule, which is about 70–80% of our body mass. Therefore, it is enormously important separately. Okay, thank you.